thank you very much. May I thank the organizers as well for this wonderful meeting. So I'm going to be talking about work I've done with Takehiro Azuma, Kota Hatayama, Yuta Ito, of course with Jun and Asato. Here we are on an 8-hour time zone meeting, working extensively. So my talk is somehow a continuation of Jun's talk. This is the IKKT model that he described in detail. It's a matrix model. It's composed by n permission matrices. 10 of them are forming like Lorentzian vectors, and 16 of them are linears. And the feature of the model that interested me more is the fact that space-time emerges dynamically from the bosonic matrix degrees of freedom, because the eigenvalues of the mu can be thought of as space-time coordinates. So this identification will allow us to study questions like the dynamical emergence of time, the dynamical emergence of space, and find a mechanism that will tell us how to compactify the extra dimensions of superstring theory using also the dynamics of the theory, as well as to define a time evolution that will permit us to study quantum performance in this context. So these are non-trivial dynamical properties of the model. First of all, time must emerge and be homogeneous and of infinite extent as we take the Larsen limit. And the number of large dimensions of space must decrease so that we have obvious correspondence with the real world and expand in a way which is consistent with cosmological models. And time and space must be real, something that is not a priori obvious. And the signature of the metric, that emergence, must be Lorentzian, at least at late time. So these are the questions that I will try to address in this talk, and I will resort to numerical computations in order to learn something about it. So lattice string theory has a long history, and started in 1999 by Jun Nishimura and Kishiya, where they studied a model which was simplified because it spreads the fermionic degrees of freedom. But then it went on with several papers studying several matrix models in 4, 6, and 10 dimensions that are related to the IKKT model, and attempting to understand the mechanism of the dynamical compactification of the extra dimensions. And what is now understood is that in the Euclidean model, the extra dimensions are compactified via a mechanism of spontaneous symmetry breaking of the rotational invariance of the model. And what we also learned in this journey is that the dynamics of the fermions are crucial for the realization of such a scenario. Unfortunately, there's a very strong technical obstacle, which is the fact that numerical simulations are hindered by a very strong complex action problem. In 2011, using a kind of perturbative expansion, the Gaussian expansion method, this gentleman here provided strong evidence that the scenario is realized, and configurations with 3 large dimensions seem to dominate the path integral by showing that the free energy of such configuration is minimal. And finally, in 2020, we were able for the first time to simulate the full model with dynamical fermions from first principles and produce results that are consistent with the result of this work. Yes?
So when you break down to the free, you also break the fancy sphere, right? So do you know if it's two-dimensional surface or is it filled in?
Well, we do very crude computations. In the four-dimensional case, the four-dimensional model here, we try to study and see how fuzzy this space is, and it was pretty fuzzy.
Okay.
It was scaling with the size of the system, but I don't know exactly. I mean, what happens in the
10% more.
Okay.
So what you see here is a simulation of the model where the effective fermionic action, which is complex, is entered in the model but with the phase ignored, the phase quench model. And even in that case, which is very close to the model that we want to simulate, we find that in the Lorentzian limit, the configurations that dominate are SO10 symmetric. And this is supported also by previous studies that show that when all the fermions are quenched, that's the original Jun Nishimura model, then also we don't have spontaneous symmetry breaking. In the four-dimensional model where the fermionic partition function is strictly positive, we also don't have SSB. And here, when we quench the phase, also we don't have SSB. But when we include the full model, then in this work, we were able to show that 3 of the dimensions of the model seem to have larger values in the Lorentzian limit compared to the rest. And this was a pretty involved computation. In order to do it, we introduced deformations to the model. First, some explicit rotational symmetry breaking terms so that we have something to teach us about the SSB as epsilon goes to 0. And because of a technical problem that I will be discussing more later, we had to introduce also this deformation to avoid the wrong convergence problem of the method that we use to do the simulations. And the model is defined first in the Lorentzian limit, then we take epsilon to 0 to see if we have SSB, and then we approach as close to the IKKT model by making this parameter as small as we can. And here, of course, the paper has many figures to support this conclusion, but here is one with this value being equal to 0.7, and where we conclude that great indications. But as Jun already remarked, in the Euclidean model, we only have three-dimensional space, and if we want to study also time, we have to go to the Lorentzian model. So the difference with the Euclidean model is, of course, we change the metric, but the action now is not positive definite. And this is the partition function here. We first integrate out the fermions, and that is the fermionic partition function, which is the Faffian that comes from out, and this is a real polynomial in A. That is an important thing valid for the Lorentzian model. But as Jun explained before, this is equivalent to the Euclidean model. And in order to study something that will be related to the Lorentzian model, we introduce this Lorentz invariant mass term, which is a deformation controlled by this parameter gamma. And we add this term to the action that we want to simulate. And this is the model that we'll be discussing in the following transforms. And of course, this is understood in a way where we first take the Lorentzian limit, and then we take gamma going to 0, but keeping gamma positive before. So, in order to make a space-time interpretation of the model, first we use the symmetry of the model and diagonalize the time matrix. So after the diagonalization, we have the eigenvalues alpha 1 through alpha n here. We have a trace symmetry, and we can always shift those eigenvalues any way we like. And the convention here is to set the first one to 0. And then we choose the rotation so that these are ordered in this way. So after that, we have no freedom to rotate the spatial matrices. And a non-trivial property of the system in the phase that we will be discussing later is that it has this strong narrow band diagonal structure, where the elements of the matrix that are close to the diagonal are much larger than the ones that are far away. And the typical length of the band is characterized by a small n integer here. And what we consider here, n is picked so all those matrix elements are considered to be small. And this n by n matrix will correspond to the coordinates of space. So if we look at the diagonalized A0 matrix, here it is diagonal, we take the corresponding eigenvalues of A0, we average them out, and we get this alpha bar here. The way that I will be defining time in the next is the following. I consider the differences of subsequent alpha bars to give us the delta t. And as we will see, this delta t can be either a real number or a complex number. So in order to define the sense of time, these delta t's are taken here and added with an absolute value to compute the time that corresponds to this space. For technical reasons, Nishimura and Tsuchiya suggested to make a change of variables, and instead of considering the eigenvalues of alpha 0, is to consider those auxiliary variables tau. So the reason for introducing this change of variables is because now the taus take all real values from minus infinity to plus infinity. And the way the definition is made, it makes the ordering of the eigenvalues always correct, no matter what the values of tau are. And this is important if we want later to use the complex Langevin method, where we have to complexify the degrees of freedom that we will be computing with the corresponding stochastic equation.
Question.
Yeah.
Why on
There is a shift symmetry, so I can shift them whenever I want, wherever I want. So I chose alpha 1 to be 0. Fix that.
I'm going to
Yeah. It is. I mean, in the original papers by Jun and Kim, and that's what we were doing. Always, they were putting the time. We're making. And later, I will also show the time to do. I will use the shift trivial. So after making this change of variables, the model that I will simulate is this one. I will integrate over the taus and the spatial matrices here. I have to add those terms because I fixed the symmetry and made change of variables here. But the technical problem that exists with this is that there are these eyes. These eyes induce in this model a very strong complex action problem that we have to deal with the available methods in the market to overcome as much as we can. So the pattern here doesn't contribute very much to the problem, but it's actually. So the complex Langevin method is the following. It's a system of stochastic differential equations where we put here stochastic variables that are random variables that have a Gaussian distribution, and it is possible to choose them real information here. There is a freedom in that, but for technical reasons it is easier to make this choice. And the derivatives of the action here are called the drift terms, and as we make the time evolution in this fictitious time, the Langevin time, then those terms antagonize each other, and the system finds itself in some equilibrium. The fact that the action is complex makes the evolution consistent only if we complexify those variables. So the taus that are originally real are becoming complex numbers, and the matrices, the special matrices here, which are Hermitian, we also obtain an anti-Hermitian part in their general n-by-n complexes. So as I said before, when the system comes into equilibrium, we can calculate and show that expectation values calculated in the time direction of the successive given time are equal to the expectation values of the original model. And this is a non-trivial result that also has its small traps. Yes. What? No, the original model is not changed. So when I put expectation value here, this is the expectation value with respect to this. So now this...
In your flow equation, how do you get...
Well, you have to compute... You have to compute the probability distribution of the time evolution here, and show that this probability distribution will give you a result such that when you make this average, this will be equal to this. Okay. Now, it is well known that this method is plagued by several problems. We have this wrong convergence problem that was studied for many years, and for many years from the original suggestion, the method was not used because of that. And this problem was, there was a lot of progress in the 2000s studying all this, culminating with these authors offering us a very simple criterion that will help us have sufficient, when this criterion is satisfied, this is sufficient to believe that this model will not give us wrong answers because, for example, the flow can go very deep in the imaginary or in the anti-Hermitian direction, or because another problem that we will be discussing soon, the singular drift problem. I think the microphone doesn't like me. Yeah, I think that's what I will do. So the idea is to make this very simple computation. This is a specific norm for the drift terms, defined very easily from this formula here. And the criterion is to perform a simulation, compute the probability distribution of this norm here. And if this is asymptotically going to zero faster than exponential, then you're guaranteed that you will not have those problems. And here I'm showing you some cartoons from our simulations where these simulations are very good. We have a Gaussian distribution of this random variable. This is failing because it goes slower. I mean, this is a log-log, a log, not log plot here. This is just normalization. It's just counting the number of terms so that it is of order 1 as you change n. It is not important because all you care is whether this goes exponentially or not. So, I mean, this is for comparing a different n, but it's not important. I mean, for the criterion, the normalization is irrelevant. Okay. So the other problem that arises here is the fact that the effective partition function enters with this term in the effective action, which involves this trace that has the inverse of the matrix M appearing here. And when the eigenvalues of this matrix accumulate near the origin, then we are in trouble. These eigenvalues don't have to be exactly 0 to have a problem. When they get very small absolute values, that could lead to numerical instabilities. So we really need to go to make them in a way to stand a minimum distance from the origin to have correct results. So Ito and Nishimura proposed, in the context of a different model that they study, to shift those eigenvalues away from the origin by adding this quadratic in the fermions term. I mean, it was not exactly that in their model, but in spirit it is the same. And this deformation here is controlled by this parameter MF. Of course, this takes us away from the original model, and in order to study the IKKT, we have eventually to send this parameter to 0. Notice also that if this term becomes very large, then it effectively freezes the fermionic fluctuations, and we obtain the fermion quenched model, or AKA the bosonic model, so the model without fermions. So here is also a cartoon of the effect of this term. I will show that figure later for more details. But you see that its effect is to take the eigenvalues of the matrix M and shift them to the right from the origin. In order to study the complex Langevin, with the complex Langevin method, the model, we have to discretize the stochastic equations, and this can be done in many ways. We have done it in first order, and also applied the second order Runge-Kutta. And of course, there is a time step here that one has to be careful in the end and send it to 0 to make sure that there are no discretization errors. The fermionic drift is computed in a way that is known very well from lattice QCD for several decades. And instead of computing this trace directly, which is time costly, we introduce a Gaussian noise normalized as here. And we compute this, this scalar here as it is. And average over chi will give us an estimator of the trace. And therefore, the heart of our computation becomes computing this product here, which is the inverse of M acting on a n² long vector. And for that, we can use the conjugate gradient method. Of course, we have to be careful because for the conjugate gradient method to be efficient, we have to have a positive definite matrix, but we compute the solution by using M dagger M instead of M. That's not a problem. Finally, we can save a lot of CPU time by realizing that the matrix M is sparse, and instead of computing the matrix vector products directly, we use this formula here, which is n cube in CPU time, and that is the dominant contribution in the simulation. Furthermore, we find that in most cases, we have to introduce the so-called stabilization parameter used by Athanasiou and Jagger in the context of lattice QCD. What we do is we introduce this parameter eta, which we keep very small, and that makes the spatial matrices a little bit more Hermitian than they are. Of course, when eta goes to 1, this is completely Hermitianizing the matrix. When eta is 0, nothing happens, and we typically keep it at this range of values. So let me show you some results. These are the distributions of the alphas, the eigenvalues of A0 for an interesting set of parameters. We have done lots of simulations, but for what I'm going to discuss today, these are the relevant ones. So this is about 64 by 64 matrices. MF is not so small, it's equal to 10. And gamma here is changing, the parameter controlling the Lorentz invariant mass term. And what you see here is that the distribution is close to the real axis. It's not on the real axis, so they're not real. They're kind of more complex near the origin, but then at later times, they tend to be parallel to the real axis. So if we consider the time to be the difference between the eigenvalues, we interpret this as having here real time and at early times to have complex time. So it kind of seems like we have a change of, I mean, it's an indication that we may have a change of the signature of the metric from being Euclidean to Lorentzian. Of course, this is not exactly Euclidean. Euclidean is this line here to compare with. But anyway, we have MF large, so we're not really simulating the true model yet. We confirm that the model has a very narrow band structure when we find it in this phase. So the space-time interpretation is holding. And we also check whether space is also real, which is also not trivial. So the parameter that we measure to decide whether space is real or not is this angle here, theta space, which is the phase of trace A squared. And if this is 0, that means that this is 0, and we conclude that space is 0. Now, this line here corresponds, according to what Jun said before, to the angle that gives us the Euclidean model. So what we see here is that we start with theta s, which is not 0 clearly, but not as big as the Euclidean model. This also shows from the slope here that we're not on the Euclidean model yet. And as we move to later times, it dies out to 0. So at late times, it seems that we have real time and real space. And another feature when we find the system in this phase is that one of the dimensions is large and it is expanding exponentially with this time. So here you see I center the time at 0 as you want it. So what we compute here, we call this the moment of inertia tensor because it computes the distribution of the eigenvalues of this matrix here. First, we Hermitianize the matrices, then we diagonalize them, we order them, and then take the expectation value. And this gives us this result. 9 of them remain small, and 1 of them starts from being small and then increasing with a law that is fitted here to an exponential quite well. So this is for MF equal to 10, and you see here the difference between smaller gamma and slightly larger gamma. We have some signal that the expansion is more prominent. Now we stay at the same gamma and decrease MF. We were able to go up to MF equal to 5, and we see that by decreasing MF, we have maybe some slight stronger expansion than when MF is equal to 10. Now, I have to stress, though, that we have seen this behavior also in the bosonic model, which you can think that it corresponds to MF equal infinity. So we think that this behavior is, the model is still in the quote-quote bosonic phase, at least for the parameters that we have computed. But it seems so far technically hard to reduce MF to smaller values. And for the values that we have simulated so far, the system remains in this bosonic phase. The bosonic phase is characterized by a strong attraction of the eigenvalues. And the effect of the fermions is to make this attraction weaker. As the number of the bosonic matrices is increased, also the attractive force between the eigenvalues is also expected to increase. We also make another remark, which is very important, is that the IKKT Pfaffian, not the deformed one, is 0 when only 2 of the bosonic matrices are non-zero. So it seems that the one-dimensional expansion that I have shown you before must be strongly suppressed when the effect of the Pfaffian will kick in. Furthermore, this is a speculation. It seems that when we have expansion, we have an exponential expansion in time. So space will, the expanding directions will be quite big if we compare them to the extent of time for given n. So if two-dimensional configurations are suppressed, then three-dimension comes next. And since time will not be one of them, we may have and obtain a three-dimensional expanding universe. So in order to avoid the problem of not being able to reduce MF further and try to enhance the effect of the Pfaffian, we have performed some simulations that favor lower dimensional configurations, which I will call d tilde, which is a number smaller than 9. Okay, 9 are the spatial dimensions of the original model. Now we'll make simulations of configurations that are mostly d tilde dimensional. And as d tilde is increased and MF decreased, we hope to see a transition from the one-dimensional behavior to the three-dimensional one. Now, the way we did the suppression was in two ways. First, one can set the remaining dimensions equal to 0 at each step. Or if we want to see in a continuous way the effect of this suppression, we can introduce a parameter lambda in this Gaussian term. And as this becomes very large, then d tilde configurations will be enhanced and higher dimensional configurations will be suppressed. And we hope that with this cooking that we're doing here, the bias will be small, expecting a low-dimensional universe to emerge. So let me show you first how this can improve the situation with MF. And of course, this is a small matrix here, n equal 22, so that we can compute the eigenvalues of the fermionic matrix M. So you see here for MF equal to 2, this is the distribution of the eigenvalues. And as we increase lambda, that means we suppress, we keep, five dimensions here, large, and the other 4 are suppressed. So as the other 4 become smaller and smaller, you see that the distribution becomes narrower and narrower close to the real axis. And that gives us hope that we can decrease MF further. And indeed, if we simulate MF equal to 0.5, then you see that this distribution is still narrow and we can avoid the origin. So let me stick now to MF equal to 2 and present you some results for n equal to 96. So what I will show you now is that as we vary the parameter gamma that controls the strength of the Gaussian, of the quadratic term, as we lower the value of gamma, we will see a transition from the one-dimensional expansion to a d tilde dimensional expansion. Of course, when gamma goes to 0 for finite n, we go back to the Euclidean model. So, there is a gamma that if we lower it further, we just obtain Euclidean model. So I'm not taking gamma very small. I keep it to the range where I can obtain real time and real space. So here you see that for gamma equal 2, I have this one-dimensional expansion here. There's also some suppression here, which is interesting to see what it is. That now is increasing gamma, and you see qualitatively the behavior is similar, although the range of time has been suppressed. This has become a little bit more complex. And then at gamma equals 6, we lose the one-dimensional expansion, and we have an SO d tilde symmetric universe. Of course, the other dimensions are artificially kept to 0. We are at lambda equal infinity here. Okay, so this might correspond to the symmetric phase of the model. Here are also some results for MF equal to 4, which are qualitatively similar. At gamma equal 2, we have one-dimensional expanding universe, real time, real space. And then when gamma is increased to 4, we have still expanding real time and real space universe, but which is SOD tilde asymmetric. So let me summarize. So what we discussed today is that the Lorentzian IKKT model can be defined by contour deformation from the Euclidean model, as Jun described. Then the two models are equivalent and the emergent space-time is complex, Euclidean and three-dimensional. We introduced the Lorentz invariance mass term using a positive parameter gamma, and we defined the model in the limit n goes to infinity, large n limit, and then gamma to 0. We simulated the IKKT model using the Complex Langevin Method to avoid the complex action problem. And in order to avoid the singular drift problem, we introduced a fermionic deformation here, controlled by a parameter MF, which should be taken in the end to 0. So we have performed simulations for MF larger than or equal to 5, and we obtain one-dimensional exponential expanding space. Time is emerging dynamical, it is homogeneous, complex at small times, becoming real at large times, and space is also real at late times. The signature of space-time is changing, possibly from being Euclidean at small times to being Minkowskian at later times. In order to simulate the model for smaller MF and enhance the effect of the Pfaffian, we simulated the model with a constraint that suppresses the dimensions larger than d in space. And we found a transition from the one-dimensional expanding behavior to a d tilde expanding behavior. Since the Pfaffian is 0 for two-dimensional configuration, the one-dimensional expansion is expected to be strongly suppressed in the IKKT model. And we hope that by further reducing MF, we can obtain a three-dimensional expanding universe. Thank you.
Supersymmetry does not.
Yes. In the end, we will need, as MF goes to 0, the model is supersymmetric. The model that we simulate, of course, I also said it is still in the bosonic phase. So it is dominated, so the effect of the supersymmetry is not seen yet. So for that, that is future work that we are trying hard to do. But this is the hope.
So would it be possible to?
Yes, in fact, they have been proposed by Anos and others, and we have tried them ourselves, but that didn't help us. So we studied them for a couple of months, but we found that for what we're doing so far, we don't see any improvement. In a numerical sense. I mean, if you write down a term that is keeping supersymmetry on the lattice, you do that because you hope that finite size effects will be smaller. Otherwise, it doesn't matter. I mean, you can write anything you want that in the continuum limit will be supersymmetric. So when you do a lattice discretization, you decide to keep some of the symmetries because you hope that that will make the discretization effects less strong. So when I say that we tried it and we didn't see any improvement, is that for the matrix sizes that we saw, we didn't see anything better coming out. Sorry, Pfaffian phase? You mean the complex phase? Yeah, okay. Yeah. Yes. No. We're not quenching anything, but, okay, the Pfaffian is the main reason for the complex action problem in the Euclidean model. Okay. In the Lorentzian model, it is real. You still have the possibility of having sign problem, but Jun has done a long time ago, when they were making their first papers, many experiments, and they have tried many configurations and say most of the time the Pfaffian is positive. That's the best I can say. No, we use the CLM, we don't care. Yeah, so, I mean, if we were doing reweighting, for example, then we would care. Or, for example, Masanori, in his papers, I think he quenches the phase because the sign problem is small. I think we had measured it in the original paper also, that you take the expectation value of e to the I gamma and see how close to unity it is. And if it is not very far from unity, then the complex action problem is small. But in our case, first of all, we don't care because we use the CLM, but also the main source of the complex action problem in this model is the I in front of the action.